Good day. Today we are going to discuss about the input impedance measurement. We will see the how to measure the input impedance of a common emitter amplifier. The procedure for measuring the input impedance, small signal input impedance, first one is we have to draw the small signal equivalent circuit diagram. Use steps 1 to 6 of small signal analysis. This one is a small signal analysis. What we have to do is we have to consider the AC sources only. We have to null the independent DC sources, and we have to treat the coupling and bypass capacitors as a short circuited one and parasitic capacitor as a open circuited one. Then we have to draw the small signal equivalent circuit diagram. It consists of small signal model of a device and its biasing elements. So this is a circuit diagram. Okay, this one is a circuit diagram of a common emitter amplifier. And already we have drawn the, how to draw the small signal equivalent circuit diagram of a common emitter amplifier. This is a small signal equivalent circuit diagram of a common emitter amplifier. So which consists of small signal model of a device. Inside the dotted lines, it is nothing but a small signal model of a device, and outside it is a biasing elements. So now we have to calculate the input impedance, and later we will do the output. We will calculate the output impedance too. So whenever the input impedance seen by the source, we can say it is a Zn. Input impedance seen by the source. Input impedance seen by the base is Zn dash. Similarly, output impedance seen by the load is Zout. Output impedance seen by the collector terminal is Zout dash. Okay. This is a small signal equivalent circuit diagram. Right? Small signal equivalent circuit diagram of a common emitter amplifier. Again, I will draw the small signal equivalent circuit diagram of a common emitter amplifier. So first we have to draw the small signal model of a device, GM V pi, and its device resistance is R naught. Input resistance of a device is R pi. Okay, this is a small signal model of a device. The potential across R pi is V pi. So you have the R1 parallel to R2 resistance. I'll take this one. So we have to short this node. So VC is independent DC source. When we stand here, R1 parallel to R2, R1 parallel to R2, biasing element. Then we have RS, VS. Voltage source VS is connected through RS. Output side RC parallel to RL. Emitter is grounded. So now here this point is output voltage V0. Now let us group this resistance. Again I will once again I will draw the equivalent circuit diagram by grouping the ground point GM V pi, R naught, R pi plus minus V pi, R1 parallel to R2, RS, VS, RC parallel to RL, and V. Okay. This is a small signal equivalent circuit diagram, right? So next one is what we have to do is remove. Second step is we have drawn the small signal equivalent circuit diagram. Now step number 2 is remove load resistance from the circuit. Remove load resistance from the circuit. RC parallel to RL we have to remove. Remove means we have to open circuit it. So I will open the RC, RL, RS, R1 parallel to R2, R pi, GMV pi, R naught. So after removing here RC parallel to RL, RL will not be in the picture. RL will combine point number 2 and 3. Remove output source from the circuit. V0 is the output source. So in the reduced circuit diagram we are removing V0. Then what is step number 4? Remove the input source with its internal resistance from the circuit. So this is the input voltage source which has the internal resistance of RS. We are going to remove this internal voltage source with its internal resistance. Now the circuit will be looks like R1 parallel to R2, R pi, GMV pi, I can group R0 parallel to RC, not RC, RL, it is RC, RC, that's all. See what next? I have removed the input voltage source with its internal resistance. Next point is connect test voltage or test current source at the input terminal. So what is meant by test voltage or test current? So whenever we want to measure the resistance value using the multimeter, so the multimeter will have its own battery. The battery will supply the current. The current will flow through the resistance. That voltage divided by current will be the resistance value. Like that only we will measure. Here Vs is we don't know about the Vs source. What we are going to do is we are going to connect the test voltage. The value may be 1 volt or 5 volt, any value. The test voltage will supply the test current that will flow through the input branches. The ratio of the next point will be the measure the current supply or voltage across the input source. Then input impedance is the ratio of test voltage by measure current or measure voltage by test current. So here you see I have removed the voltage source, so I have to connect the test voltage. Test voltage means known voltage, any value. It may be 1 volt or 2 volt, anything. I connect test voltage. Now it will supply some test current, let me say IT. The IT will flow through two branches, I1 and I2. What is the input impedance Zin? Zin is the ratio of Vt by IT. Okay, I can say IT equal to I1 plus I2. What is I1? Vt by R1 parallel to R2 plus Vt by R pi. That is IT. So what is Vt by IT? Vt by IT is, so here when you cross multiply R1 parallel to R2 parallel to R pi. Input impedance Zin equal to R1 parallel to R2 parallel to R pi. This is the input impedance of a common emitter amplifier. Next one is input impedance seen from the base terminal. How can we measure the input impedance seen from the base terminal? By neglecting the biasing resistances R1 and R2. Now we are standing here. We want to measure this input impedance. So we have to eliminate or neglect these resistances in the left hand side. Okay. So while drawing the small signal equivalent circuit diagram, we have to omit the R1 parallel to R2 combination. Once again I will draw the circuit. Now the circuit will be R pi, GMV pi, RC. Okay. So we have to repeat the procedure. I follow the step number 1 to 4. Okay. And I have neglect the biasing resistance R1 and R2, R1 parallel to R2 combination, because we are going to measure the input impedance seen by the base terminal. Okay. Now what is the next one? Fifth one is we have to connect the test voltage. Here you see signal is voltage source. So I have to connect the test voltage. In case signal is current, we have to connect the test current. So VT. Okay, now the current is IT that flows through R pi only. So we can say VT by IT is nothing but R pi, which is nothing but Z in dash. Okay, Z in dash is the input impedance of the base terminal of a common emitter amplifier. Z in is the input impedance seen by the source. Z in dash is the input impedance seen by base terminal. Okay, input impedance seen by source terminal is R1 parallel to R2 parallel to R pi. Input impedance seen by base terminal is R pi. Right? So next one is we are going to measure the output impedance. So this is a procedure for measuring the output impedance. Step 1 is draw the small signal equivalent circuit diagram by using the small signal analysis, procedure of the small signal analysis. Next one is null the effect of input source along its internal resistance. Then third one is remove load resistance RL from the circuit. Fourth one is remove output source from the circuit. Fifth one is connect test voltage or known voltage or test current, known current at the output terminal. Measure the current supplied or voltage across the output source. Then determine the output impedance Z out equal to R out, which is nothing but a ratio of test voltage by measured current or measured voltage by test current. This is a circuit diagram. In this circuit diagram, you can see Z out. Z out is the output impedance. Z out is the output impedance seen by the load resistance. Z at bar is the output impedance seen by the collector terminal. By following the midband gain analysis or small signal analysis, we have drawn the small signal equivalent circuit diagram. Now let us apply the procedure. So step number 2 is null the effect of input source along its internal resistance. This is the input source along its internal resistance. We have to nullify it. How can we nullify this input source along its internal resistance? Since it is a voltage source, we have to short it. Here we have to short it. Then remove load resistance from the circuit. We have to remove this load resistance from the circuit. Then remove output voltage source from the circuit. We have to remove the output voltage source from the circuit. Then, so first we will do these two things. R1 after this one we have to kill. We kill this point. That means we nullify the voltage source along its internal resistance. You can write R1 parallel to R2 parallel to R pi as RB. Okay, here we have the potential of V pi. This point also grounded. GM V pi. R0 RC. Okay, so we have two kinds of output resistance. One is output impedance seen by the load Z out. Another one is output impedance seen by the collector terminal Z out dash. Okay, while calculating Z out dash, we have to ignore the RC resistance. Right? So now what is the next step? Next step is we have removed the load resistance RL, remove the output voltage source. Now we have to connect the test voltage or test current. Here you see we have removed the voltage source. So we have to connect the test voltage VT. which is supply the test current of IT. Now look at the circuit. RB, let us say this is node A and node B. Both node A and node B are grounded. So V pi will be 0. There is no potential across RB. You can say V pi will be 0. So GM V pi is the dependent current source. GM V pi is the dependent current source. This current depends the input voltage. When V pi equal to 0, GM V pi will be 0. So current source 0 means it is open. Okay, voltage source 0 means it is shorted. Current source, dependent current source 0 means it is open. This is R0, RC, and we are connected with the test voltage VT, which will supply the current IT that will flows through I1 and I2. So what is IT? IT is a summation of I1 plus I2, which is nothing but VT by RC plus VT by R0. So Z out is a ratio of VT by IT, which is nothing but R0 parallel to RC. So now this is the output impedance of a common emitter amplifier. So next one is output impedance seen by the collector arm by neglecting the biasing resistance RC. So again same thing, V pi 0, then GM V pi is 0. So what else? You have R pi, GM V pi is opened, and we are going to connect the test voltage VT here. That will supply the test current of IT. So Z out dash, here when I measure it is Z out dash. Z out dash is nothing but, sorry, it is R0, not R pi. Z out dash is nothing but R0. Okay. So now you see output impedance R0 parallel to RC when output impedance seen by the load circuit. Output impedance seen by the collector node is R0. Okay. Just let us take the one simple table. Common emitter amplifier. For common emitter amplifier, so what is the Z in dash? Z in dash we can say R pi. What is the Z out dash? Z out dash we can say R0. We can say common emitter amplifier has no AC feedback. Okay. So later on we'll discuss about the other amplifier which will have the AC feedback. So we will always compare other amplifier with common emitter amplifier. Okay. So common emitter amplifier we can say there is no AC feedback. Other amplifier, for example, common emitter with emitter resistor amplifier will have AC feedback. Common collector amplifier will have AC feedback, and common base amplifier will have AC feedback. We always compare feedback amplifier with without feedback amplifier, AC feedback amplifier with without AC feedback amplifier. So what is the voltage gain of this one? GM into R0 parallel to RC by ignoring the load resistance. This is a voltage gain of a common emitter amplifier, GM R0 parallel to RC. Later on we'll make a comparison chart. We'll compare the performance of the each and every amplifier. Thank you. So next class we'll discuss the common emitter amplifier with emitter resistance. Thank you.